Hello everyone and welcome to this lecture. So now we need to discuss some practical aspects of deep learning. The first aspect is neural network architecture search. So unfortunately there is no clear guidelines to help us choose what's the best network architecture for a given problem we're trying to solve. So picking the right architecture often comes down to experience. Essentially, you've tried a lot of different architectures before and good judgment as well. So from early on with neural network, there have been some research to try to automate the process of architecture selection. Essentially, we can think of selecting the architecture as another hyperparameter tuning problem, similar to finding the optimum learning rate, for example. Okay, but in this case, the hyperparameters we're interested in determining would include the depth of the neural network, the width of the neural network, the type of connectivity, and other attributes like activation function, for example, regularization, and so on. However, there are so many choices to be made that just a simple grid search would take too long, essentially, to test every possible combination of hyperparameters that determine the network architecture. Therefore, it's common to use what's called neural architecture search to explore the state space of possible network architectures. Many of the search techniques and learning techniques we covered earlier in this class can be applied also to search the different neural architectures, options we have. So one example for that is very often used includes evolutionary algorithms like genetic algorithm, for example, because essentially that would involve joining parts of two networks together. Okay, essentially, and mutation, which in this case would involve adding or removing a layer or changing a parameter value. So these are perfect features for genetic algorithm type approach to find the ideal network architecture for a given problem. We can also use hill climbing, okay, with similar mutation operations. We can also use Bayesian optimization. Some people have used reinforcement learning. We will discuss reinforcement learning later in this class. All of these are search or optimization methods that could be used to identify the ideal network architecture. Another possibility is to treat the architecture as a continuous differentiable space and use gradient descent essentially to find an optimum solution. Even if it's not a global optimum, it's still locally optimum solution. For all these search approaches, the major challenge obviously is how to evaluate a given candidate architecture. So the straightforward way to evaluate an architecture is to train it on the test set for multiple batches and then evaluate its accuracy on a validation set. But essentially, if we keep doing that over and over, that would take multiple GPU days. So there have been many attempts to try to speed up this estimation process by eliminating or at least reducing the time it needs to complete the training of the network. For example, we can train on a smaller data set we can train for a smaller number of batches and predict how the network would improve with more batches. We can use a reduced version of the network architecture that we hope is a good representation of the full version, but essentially to allow us to make a quick decision whether or not to keep going in this direction. We can train one big network and then search for subgraphs of the networks that perform better. Another approach is to learn some heuristic evaluation function. Okay, so for example, A* search. So essentially we start by choosing a few hundred network architecture, train and evaluate them. So this gives us pairs, right? A given network and a given score for that network. Then learn a mapping from the features of a network to a predicted score. So essentially try to create a function, create a score that is a function of the network architecture. And then from that point on, we can generate a large number of candidate networks and quickly estimate their value using this heuristic evaluation function. After a search through the space of networks, the best ones can be evaluated using a full complete training procedure. Okay, so that would be also a shortcut that would help us avoid spending days to look for a network architecture. Another important element, as we saw before, is regularization. And the key here is to always remember that our ultimate goal is to do well on unseen data. So the generalization aspect of the problem. And in order to generalize better, we have to avoid overfitting to the training data. So we saw before that regularization, which essentially limits the complexity of a given model, can help a lot with generalization. So this is true for deep learning models as well. And in the context of deep neural network, we typically use what's called weight decay. Okay, so weight decay essentially consists of adding a penalty term, which you can see here, lambda times the summation of the squares of the weights of all the neurons in your network. We add this penalty to the loss function used to train the neural network, where lambda is a hyperparameter that controls the strength of the penalty. And of course, the sum is taken over all the weights of the network. So the higher the lambda, the more regularization you're forcing, and the lower the lambda, the less regularization you're applying. If you plug in lambda equals 0, you get back your original loss function, which is essentially there's no penalty and there's no weight decay. So the bigger the lambda, the smaller the weights that will be used in the network. Okay, so typically lambda is in the range of 10 to the negative 4. Now, choosing a specific network architecture can be seen as an absolute constraint on the hypothesis space, because once you decided on a given architecture, you reduced a lot the entire hypothesis space. So a given function is either representable using this specific architecture or it's not. Loss function penalty terms like weight decay offer a softer constraint because you start with a network with many neurons, and then you let the training process eliminate neurons that are not adding to the learning process. Okay, so it's a softer constraint because functions represented with large weights are in the function family, but the training set must provide more evidence for you to choose the specific function. So essentially, if the training shows that certain weights are not adding values, this means that automatically the function will decay, the weights will decay with training, and this complex function will be eliminated from the hypothesis space. Now, interpreting the impact of weight decay in neural networks is not straightforward. In networks with sigmoid activation function, for example, we assume that weight decay helps to keep the activation near the linear part of the sigmoid, which essentially help us avoid the flat operating region, which is the cause of the vanishing gradient. If you're using ReLU activation functions, in that case, weight decay is also beneficial, but the explanation that makes sense for sigmoids doesn't apply here because the sigmoid, the ReLU output is either 0 or 1. So there's no really flat period where you're forcing the weights to operate at. So even though it's not really clear why weight decay works, it does work. Okay, and one possible explanation is that weight decay implements a form of maximum posteriorly learning. Okay, so for example, if we assume that X and Y stands for the inputs and outputs from the entire training set, the maximum a posteriori hypothesis HMAP satisfies this requirement. So the first term is the usual cross entropy term right here. The second term, log of P of W, prefers weights that are likely under a prior distribution. So this aligns perfectly with the goal of regularization and the penalty term, which means essentially that log P of W is equal to negative lambda of the summation of Wij squared, which means that P of W is a zero mean Gaussian prior. So regularization using weight decay is very popular, but there are other ways to do regularization by approaching the problem by eliminating completely nodes that might not be adding value to the neural network in a process similar to ensemble learning that we've discussed before. So let's talk about the second approach in the next part.